This is part 2 of my survey of Chesil Beach. In part 1 we walked a 10-mile stretch of the beach, stopping every 500 metres to pick up a standardised cupful of stones, which we then weighed, measured and recorded. Today we're going to look at the recorded data and see what we can learn from it.
So this is Chesil Beach. We're on the land side of it, on the Fleet Lagoon side of it. We're just going to go up to the top of Portland there, the Isle of Portland, where there's a viewpoint, and hopefully, if it's not too windy up there, I'll be able to tell you what this project was all about. So up here on the northernmost tip of Portland Island, that is Chesil Beach. It's a huge bank of gravel that extends from here 30 kilometres all the way to Seatown, West Bay at the northwestern end. That's about nearly 20 miles. There's about 10 miles of it here that stretches from Portland to Abbotsbury, that's cut off from the mainland by the Fleet Lagoon. So there's this local legend that fishermen and sailors beaching on Chesil Beach, on that part of the bank there, in fog or at night, would determine their location by picking up a handful of stones and examining the stones, and they'd be able to figure out where they are. So we're hoping to test that legend. It is true that there is a continuous gradient of size of stones. Large potato-sized cobbles here at Portland, pea-sized shingle at Abbotsbury, and a continuous grade of stones all the way along. In the previous video we surveyed that. We stopped at 500-metre intervals all the way along the 16-kilometre stretch here and sampled, measured, weighed the gravel. We've got that in the spreadsheet. In this video we're going to be doing the science on it. We're going to look at what the graphs look like, and we're going to see if we can actually figure out whether we could find our way. Based on that data, we can find our location on the beach from a sample of gravel. That's the plan. That's what this video is all about.
It took me a couple of hours to bash the written records into a spreadsheet to analyse them. Each tab comprises the raw numbers for each of the 33 measurement positions. Then I've added some calculated fields for weight and bounding cuboid volumes, remembering to subtract the 13 grams weight of the sample pot. I copied the main table of measurements across to the right, then sorted it descending by bounding cuboid volume. This allows me to calculate averages of both the unfiltered values, but also to calculate another average after discarding the biggest 2 and smallest 2 stones, and actually biggest 4 and smallest 4. So just an average of the middle 8 or 4 measurements when ordered by size, the largest and smallest stones in the group being the ones most likely to be anomalous outliers. Remember, we are trying to measure the typical stones at any given sample point. This is a fairly common method for denoising of data for analysis, but it's just an option. The whole original data is still there too. So let's have a look at some charts. Firstly, the count of stones per sample. This is just the number of stones that would fit to level with the brim of that plastic tub I used. This, I believe, is proportionally representative of the number of stones that would be in any consistent handful that somebody might pick up to look at. And that notion is the core of what we're testing here. The local legend that sailors beaching on Chesil Beach would be able to pick up a handful of stones and by looking at them judge where they were. And this does show a pretty consistent trend. At the Abbotsbury end of the beach you have hundreds of stones per handful. At the Portland end of the beach you have single-digit numbers. And there is a shallow curve of change between those 2 points. By the way, I'm not necessarily going to use the conventionally most appropriate chart type for these numbers. Some of these should probably be bar charts or something else. I'm choosing these not for appropriateness but for ease of viewing in the video. If you want to chart it the way you feel appropriate for the data, the spreadsheet's available for download from a link in the video description. The counterpart of this chart is the total weight of pebbles in the cup, which, by the way, although it originally contained 300 ml of cream, is actually 375 millilitres in capacity, just because it had some headspace when it was filled with cream. Not very sure this chart is even useful, but here it is in case it is. It shows, I think, a slightly descending trend, which might just be an artefact of the efficiency loss of trying to pack increasingly large objects into the same size small container. There is an interesting jump right at the end, which I believe represents a real-world anomaly rather than error or noise. Right at the Portland end, the composition of the pebbles quite abruptly changed from predominantly flint and chert to predominantly quartzite, which is a more dense mineral, and this was even noticeable by hand when we were measuring. Despite only being able to fit 8 rocks in the cup at sample point 33, and with fairly large voids between them, the cup still felt noticeably heavier in hand than any of the previous samples. And that's what I think you're seeing on this chart. One other thing to look at is the volume of the cup divided by the sample count, which gives us the rough packed volume occupied by each pebble. This is not necessarily exactly proportional to the bounding cuboid volumes, since different shapes of objects will pack together differently. Now, this is really nothing more than a slightly different way to view the sample count per cup, but anyway, here it is. Here's the average weight per pebble in the whole sample, again showing a fairly recognisable curve. And the obvious next thing to do is look at the average volumes of the bounding cuboids, that is, based on the measurements of 12 pieces selected as impartially as possible from the whole cupful. So it's important to remember we're comparing a subset to the whole set here, but it shows pretty much the same curve. The bounding cuboids are in cubic millimetres, that is microlitres, and I can't be bothered to convert, so I just adjusted the scale so they're represented equally here. And then we can overlay the bounding cuboids on the raw packed volumes like this. Here's the bounding cuboid plot with the top and bottom 2 size samples excluded, and with the top and bottom 4 samples excluded. Doesn't make a whole lot of difference, which I think mildly supports the notion that the measurement data was fairly clean. Looking at the component dimensions of the pebbles does tease out a few interesting things, including this anomaly at sample point 4, where we noticed even by eye that the stones got smaller here before they started getting bigger again further along the beach. This area from sample points 12 to 15, where the length of the pebbles remained more or less the same, but their width and thickness continued to increase. Again, we perceived this when we were measuring. Not only did they appear more chunky to look at and handle, but they were rounder, and they had a greater tendency to roll away on the tray while we were trying to count them. These similar points surround the sample points numbered in the low and high 20s, where again the overall proportional shape of the pebbles was distinctly changing. These changes were physically perceptible as we were handling the stones, and we both noticed and commented on them as we encountered them. So these graphs all show a sort of similar picture. They would, of course, as they are really just slightly different ways to look at the same data. And from this data, and from our experiences on the day, I think we can say there's a nearly continuous change in observable properties of the stones along the beach. And I think it's a sufficiently marked difference for a very experienced person to probably judge their location with worthwhile accuracy. And on reflection, there's definitely a requirement for that. Just because of a significant lack of visible local landmarks, when you approach Chesil Bank from the sea, the gravel bar towers over you to a height of about 15 metres, obscuring the mainland behind it. And it's not much use looking towards Portland or Seatown, as those landmarks may be miles and miles away. And indeed, for a quite long time on our walk, it didn't seem like Portland was getting any bigger in our field of view, even though we knew we were making headway on the map. So whilst we can never say whether the ancient sailors actually did use the pebbles on the shore as a sort of low-tech GPS, I'm of a view that it's plausible to say they could have done. And not just to determine which end they were at, in order to get to the mainland, but maybe also to find their way to a hut on the leeward side of the bank, or the place where they might have moored another boat to cross the lagoon. But that's just an opinion, right? Well, sure, but let's put it to the test, because while we were walking on the beach, my friend collected 4 samples of rocks and gave them to me at the end of the walk. I don't know where he picked them up. We did plan to do this, but he was subtle enough in his sampling activity that I genuinely have no idea where he picked these up. But he has the exact locations saved. So let's go over to Studio Shrimp now to take a look at those samples. We'll measure and weigh them using similar methodology and compare them to our survey data and try to pinpoint where they came from. Then, and only then, will my friend release the actual location data to me, and we'll see how close I actually got. So, I have here 4 samples of pebbles from Chesil Beach. Quick note from Editing Shrimp. It's forbidden to remove stones from Chesil Beach, so I should not really have brought these home. It was for science, but it was still something people aren't supposed to do. Keep watching though, as I'll try to make this right a bit later, and I humbly beg forgiveness for breaking the rules in the name of amateur science. There are 3 bags. I might have a little clue about where that one came from because the ink has run. But anyway, I prepared 3 bags and gave my friend 3 little pieces of paper to put in them. He actually collected 4 samples and put one of them in a crisp packet. So we got 1 more sample than I intended us to get. However, I don't know where these came from on Chesil Beach. Like I say, that one, I might have a little tip on that one because that ink has run, which means those pebbles went in the bag. They look a bit wet, so that might have been the point where it rained. So if I'm accurate on this one, you can accuse me of cheating because that could well be around about here. But we got the other 3 anyway to try and evaluate. So all we're going to do here is the same as what we did on the beach. Just first check my cup is 13.3 grams. So my sample is 240.1. And this is sample number 1. I might just tip out the seaweed and stuff first before we weigh it. There's a piece of plastic litter.
as well. Let's get rid of those bits. And then the actual pebbles can go back in the tray. So we've got 238.3. Now what I don't have is the advantage of somebody else writing down what I measure. So what I'm going to do here is the same as what we did, but I'll read out the measurements and then I'll have to transcribe them off the video footage. What it's pointless to do here is count them because we haven't got a full cup full. That would have been a really easy way to get a great sort of bearing on where these came from. But anyway, I'm just going to take a small handful of stones and I'm going to measure 12 from this sample. So we've got 18.16, 13.72, 8.43, 14.93, 11.08, 7.80. So that concludes the measurements for sample number 1. Actually, of course, I do have to count them because I want to calculate the average weight per pebble. Okay, there are 140 pebbles in sample number 1. So I'll put those back in the bag in case we need to do any further measuring or anything later. Next, we come to sample number 2. Yeah, and this one I think the pebbles are actually still wet, even though it's a couple of weeks later. So this one, well, I suppose that only guarantees it was after the point where it rained, or maybe I'm fooling myself. Maybe he picked them up from the shore when we went down there. Who knows? Anyway, 236.7. And these are noticeably larger. So yeah, just my kind of rough judgment. I would say that one came from the first quarter of the beach. That's somewhere near the Abbotsbury end. Somewhere perhaps in the first 5 samples. That's sample number 1. Sample number 2, I would say, was in the second quarter. So somewhere between, like, you know, maybe 8 to 15 or something like that sample point. Anyway, let's count them. And actually the reason being, these are a little bit chunkier and they've got that kind of thing where they roll. 18.43, 13.40, 8.92. Sample number 3, now I would say that came from past halfway, perhaps even 2/3 of the way along the beach. 31.38, 19.35, 11.17. And then sample number 4, unconventionally packaged, is larger again. I think these are larger pebbles. And I would say again, last quarter of the beach perhaps. Let's just measure that. 281.8. And we have 20 pebbles. 26.99, 20.96, 14.08. That's our 4 samples. Now I've got to go and just transpose that data into the spreadsheet and make my calculations and guesses on where these were picked up from. I do believe that samples 1, 2, 3 and 4 were picked up in that sequence along the beach, which is interesting. I didn't expect that that would necessarily be the case. Also to mention, we did find a couple of pebbles lodged in our boots when we came back, so we've got another 2 stones, but I could probably tell you roughly where that came from. I would say that came from around about the 1/3 mark on the beach. Anyway, off to the spreadsheets now to figure out where these stones came from. Now, of course, the ancient sailors beaching on the shore there would not have had spreadsheets and calculators and calipers and scales and all of these things to measure the pebbles. But what they would have had is a wealth of daily experience. And so I'm kind of substituting that daily experience for some empirical measurement. I think that's a fair thing to do. We are, after all, testing whether the thing's possible, not how it's possible. You know, I think half a lifetime of handling the pebbles on the shore is probably going to create a lot of familiarity with the lay of the land, and I'm substituting a spreadsheet for something like that. Anyway, back in a moment. Okay, so these are my guesses. I've just gone through and compared these to this data here. So I've got the collation data, which is all of that table.
I bashed my sample data into different sheets and did pretty much the same calculations as I did on the real data. I've then transposed those totals here, so average weight for my samples, average cube, and then average cubes excluding 2 and 4 outliers, top and bottom. And these are my guesses. The first one I had to make 2 guesses, and I'll show you why. So this 1.609 could fit in here in between 2 and 3, or it could fit in here between 4 and 5, or it could fit here between 3 and 4, because we had that thing where the sizes went down again and up. And so this sample 1 could be there, it could be on this edge of this one, or it could be on that edge of that one. However, we've got also the average cube data to look at, as well as the weight. And there was a little bit of wobble and variation, and that will be to do with the shape and profile of the pieces a little bit. So a long, thin, flat piece might be quite light, but it will still have a larger average cube, bounding cuboid, just because it wastes a lot of space inside the cuboid. Anyway, my guess for number 1, my best guess is between 3 and 4, nearer to 4. So here. My second guess, if I'm allowed one, is it's between 1 and 2. We will see. Yeah, no, I think between 3 and 4. Just because that bounding cuboid is also between those two values there, between 3 and 4. We won't know until we know. Sample 2, I'm relatively confident that that is between 11 and 12, and it's actually about 2/3 of the way between 11 and 12, just because of where these values fall in this comparison. Sample number 3, I would say between 23 and 24. Soon after 23, though, I think 10.543 is quite close after that. So yeah, so I'm going to say soon after 23. And then for sample 4, I've got between 25 and 26, slightly further than halfway, just by virtue of, no, actually, I think about 1/3. No, I'm going to say halfway. So I still don't know whether these are right or not. So now I've got to pinpoint these on the map, send those map screenshots to my friend, which will have their coordinates, and then he will send me back the screenshots he took, and then we'll see how far off we are. I think we're probably going to be not that bad, apart from maybe number 1. Anyway, time will tell. Back in a moment. Okay, so I made my guesses and sent my screenshots to my friend, and in return he sent the screenshots he took of his map at the sample points, and the results are remarkable and completely surpassed my expectations. In fact, you might find some of these difficult to believe, but I can only assure you we were completely rigorous about keeping me blind to the source of the samples until right now. For sample 1, I guessed it was here, opposite Abbotsbury Swannery. I'll overlay and transfer that point onto Google Maps like this. Here's the actual screenshot of the sample point, and when we overlay that on the map, the blue dot is the actual sample point. It's about 100 metres away from where I thought it would be. That's a pretty good result, especially as this was the least certain of my guesses. The next one, again onto Google Maps, I placed this just opposite Coast Guard's retreat. The actual sample point was here, about 300 metres further along the beach. Still pretty close, I thought. Sample 3 was the one that made my jaw drop. I placed it here, just past the Portland boundary stone. The actual sample point was, well, yeah, pretty much exactly there. That's about 25 metres away from my estimate. And sample 4 I placed here alongside White Regis. The actual sample point was about 250 metres further along. So my average error distance was about 170 metres on a 16,000 metre stretch. That's an error of only just over 1%. And that's actually a great deal better accuracy than I could have expected or hoped for. Another way to look at that is if you shrunk a map of this part of Chesil Beach to 10 centimetres long, we would have almost millimetre accuracy of placement. Of course, as I say, I had the benefit of spreadsheets and measuring equipment that's all precise to fractions of millimetres and grams, which the fishermen of legend did not have. But they had years and years of experience of boots on the ground in this locality, which I don't have. So I think that's a wash. We can never say for sure whether they did use the rocks for navigation, but I think we just clearly proved they could have. Now, the astute amongst you may have observed that we should not have removed these pebbles from Chesil Beach. There are various laws and regulations and bylaws which forbid that, And these rules are sometimes enforced. Notably, author Ian McEwan mentioned in an interview that he had kept a couple of handfuls of pebbles that he collected here for inspiration writing a book with Chesil Beach as the setting. He was invited by Weymouth and Portland Borough Council to return the stones in order to avoid being fined. And this happened to other people too. The council doesn't want people removing the stones from the beach, and they're quite willing to make examples of people who do remove them. So I'm now going over to Roving Shrimp, who's back at Chesil Beach.
So that whole gravel survey thing we did took place in the first week of September. It's now the 18th of September. We've been away, we come back. We've done the science on the stones. We're back at Chesil Beach to put right a wrong. But first I want to get up on top of the bank because there are a few more things to talk about. Oh, by the way, while we were here, the tide is actually falling, so it's a high tide and it's falling. I took some footage of the flow out of the lagoon, out of Fleet Lagoon here, under Ferry Bridge, just so you could see what the tidal flow looks like in and out of this lagoon that's behind Chesil Beach here. So we're close to the Portland end today for the returning of the stones mission, near the visitor centre here. And this is Chesil Beach. But we've got to get the other side of that big bank there. So as I say, the tide is in at the moment, or going out. So I can't really show you the full extent of the beach. It does go down a bit further under the water at the moment. Anyway, we're just going to get over there, get out of the way of these people fishing. So the gravel bank here is quite steep, and I will talk about why that matters in a minute. But actually, while we're here in a slightly more sheltered bit here, just to mention, I asked a rather naive question when I was doing the actual walk, when we started out the walk, which was, do storm waves overtop this beach? And the reason that's a naive question is, how else did these stones get here? These stones are here and all piled up like this because the sea made that happen. So when storms break on this beach, the waves wash the gravel up into this massive heap here, this 15-metre tall bank. So the answer is yes, of course storm waves do overtop this beach, because how else did the beach get here? Anyway, we're down here close to the high tide mark now, and I'm probably not going to go any further than this little shelf here, even though it's a fairly calm day. I don't think I need to go, well actually no, let's go a little bit further down. So here's the question. Why would sailors in days before GPS need to know, from the size of the stones here, why would they even want to know where they were on this beach? Why wouldn't they just have a look at the mainland and see where the landmarks are? Well, we're at the Portland end anyway, so it's a little bit of an unfair comparison. Obviously I know I'm near to Portland because I can see Portland is really close. But when you're in the midpoint of this beach, it's not so easy to make that judgment. We walked for hours and Portland just didn't seem to be getting any closer. And so why not look at the mainland for landmarks on the mainland? Well, that's what you see when you land here on the beach. And this is at high tide, by the way, so at low tide it's even further down. That's what you see, is just gravel and gravel. And so wanting to know where you are on this beach is not the same as knowing where you are on this beach. Now, the obvious question following that on is, okay, well, why don't you just go to the top of the beach here and have a look for some landmarks? Well, that also is not quite as easy as it might seem. I'll show you that in a minute, but first we've got a job to do. So these are the stones from the samples that we picked up at 4 different points along the beach here. I'm not going to return them to their place of origin, their exact place of origin, even though I do know where that is, just because that would be a 10-mile hike. and I'm not up for it. I've only just finished nursing the blisters from the last one. So here we go. This is me returning the stones to Chesil Beach, and it doesn't matter all that much, I don't think, that they're not in the exact place we picked them up from, because we know that nature takes care of the sorting of the gravel on this beach. Nature takes care of the ordering of these stones. We've kind of proved that already. Anyway, yeah, the question was, why don't you just hike up to the top of this beach and have a look for landmarks? Well, I'll show you now why that's perhaps not as easy as you might think. So yeah, climbing up this bank, because this is gravel pretty much at the angle of repose for gravel, every couple of steps you take forward, you slide back one. Oh. So just getting to the top of the bank here is quite exhausting, and if the answer was, sorry guys, we're in the wrong place, we need to go back and row another mile that way, obviously that's something you wouldn't want to do.
Okay, people might scoff at the notion that removing a handful of pebbles from such a vast beach is harmful, whereas others might invoke the saying, yes, but what if everyone did it? And interestingly, we are in the fortunate possession of some empirical data that might help us calculate what would actually happen if everyone did it. What would be the impact on Chesil Beach if every human being in the world took one pebble? A couple of points before we get to that. Firstly, Randall Munro of XKCD has already done the maths on what would happen if the entire population of the world chose to gather in one place at one time. I won't spoil that too much, but suffice it to say it's not a good outcome. Links in the video description to that. I'll be ignoring the actual effects of people travelling places to do things. For the purposes of this inquiry, we'll assume that curious aliens magically teleport one stone from Chesil Beach directly to each living human on the planet, at their own energy expense and with no impact other than the removal of the stones. Secondly, just to note, however this calculation comes out, it's not an endorsement or encouragement to break the prevailing rules and laws about taking the rocks from here or anywhere else. I'm just curious to know what would physically happen if everyone did. We might as well, we have the data. So Chesil Beach is in total about 19 miles, or 30.5 kilometres long, from the northwest end at West Bay down to the Isle of Portland. But this calculation will ignore everything north of the Abbotsbury starting point for our survey, and we're just looking at the Chesil Bank where it detaches from the mainland, from Abbotsbury down to Portland. It's almost exactly 16 kilometres in length, including the slight curve. The cross-sectional shape of the beach is fortunately very consistent across the whole of that 16 kilometres. It's pretty much like this, a broad trapezium with another one stacked on top of it. In reality, it's a bit more complex than that, but this is a close enough approximation for this purpose. The base at sea level is about 120 metres across, the total height is about 15 metres, and the angles on the sides are dictated by the angle of repose for the gravel. So these are the dimensions, and anyway, I'm going to assume that the whole bank above sea level is made of gravel. This is mostly true, as the sea washes right through it, but it's possible that if you dug down you might encounter sandy gravel or gravelly clays or something else. I haven't taken core samples, so my calculations will be based on the naive assumption that the entire bank is solid gravel. This doesn't affect the conclusions we're going to draw anyway. So the cross-sectional area of the beach is approximately 967 square metres. Multiply this by the length of the part we surveyed, which is conveniently 16,000 metres long, and we get 15,480,000 cubic metres. Multiply that by 1,000 to get litres, we get 15.48 billion litres in volume, which is interestingly close to double the estimated population of the world. So one way to look at this was that if we shared out the whole of Chesil Beach, or that part of it, equally to every living human in the world, everyone would receive a box containing a little bit less than 2 litres of gravel each, containing an average of 669 stones. And so a rough and ready way to get a handle on the impact of each and every person taking one pebble each is to imagine taking one pebble out of that box of gravel that's a little bit under 2 litres in volume. But let's crunch the actual numbers. We know the volume of the sample pot that I used is 375 millilitres, and we know that across the sample range it held an average of about 133 stones. So we can infer that Chesil Beach contains, on average, about 354 stones per litre of volume. And from that, we can estimate that the total number of stones on that section of the beach is nearly 5.5 trillion. This estimate is wildly different to the 180 billion number that you'll get if you Google how many stones are on Chesil Beach. But I don't know who estimated that and how they estimated it, although it is apparently for the whole of the 30-kilometre stretch. I don't know. I know my figures are not going to be exactly correct. We are extrapolating from a pot the size of my fist, but that shouldn't account for orders of magnitude of difference. I don't know, what do you think? I feel like 180 billion is way too small a number, and I'm inclined to say that that number is wrong. In fact, if you Google the volume of Chesil Beach, you get 60 million cubic metres, which is reasonably consistent with the 15.5 million cubic metres that I calculated for the 10-mile section we surveyed. And anyway, if we were to assume that these two numbers, 180 billion stones and 60 million cubic metres, were both correct, that works out to only 3,000 pebbles per cubic metre, which is clearly wrong, considering we got over 400 of them in my little cream pot at the Abbotsbury midpoint, and even at sampling point 33 near Portland, our data works out to over 21,000 stones per cubic metre. So yeah, I'm going to say that 180 billion pebbles number is completely bogus, and run with the numbers I have here. So anyway, if everyone on the planet was given one stone, there would still be nearly 5.5 trillion stones on Chesil Beach. 0.15%, that is 3/20ths of 1% of the stones would be missing. Working backwards from the cross-sectional area of the beach, that works out to about 24 metres of beach gone, about one blue whale, which if it was taken all from one section would look something like this. The total amount of gravel taken would fill a cube less than 30 metres, or 3 London buses on each side, or would fill about 9.25 Olympic-sized swimming pools. Another way to look at that is, remember that bit where we shared out the beach to everyone and they all got 669 stones? Well, that's another way of saying that this little bit missing here is 1/669th of the 16-kilometre stretch, or in order to remove the whole 16-kilometre stretch, everyone in the world, including babies and children, would have to take 669 stones each. So, what if everyone did it? Well, obviously not everyone would, but if everyone in the world took one stone from Chesil Beach from random locations, I think it would be very hard to notice the difference, and very likely the loss would be replenished by nature in fairly short order. The height of the beach, for example, is not likely to be limited by the available supply of gravel offshore, but rather by the maximum energy and crest height of the storm waves that wash the gravel up there. Okay, but perhaps this hypothetical is all a bit too silly. So what if, instead of the whole population of the world, it's just the number of people who actually visit Chesil Beach? That number is estimated to be 150,000 per year, and since I earlier cast shade on widely repeated statistics, let's just sense-check that number. It works out to be an average of 411 people per day, which on the face of it seems low, but consider that includes the winter time when only a very few intrepid or foolhardy people come. So that could look something like way more than 1,000 people per day in summer, and less than 100 people per day during the most severe weather days of winter. Anyway, let's run with that number. If it's actually 300,000, all you need to do is double or half the following conclusions. 150,000 people removing one random stone each would obviously be 150,000 stones per year. Based on our average of stones per litre, that works out at about 423 litres of stones per year. So a cube about 75 centimetres on a side, basically less than half of one of those cube bags of gravel. That's how much of the beach would be removed each year if everyone who actually visits the beach pockets one random stone each. At that rate of depletion, assuming no replenishment and based on the numbers from this video, the visitors to the beach would have completely removed the whole of that 16-kilometre stretch of Chesil Beach right down to sea level after 36.5 million years. Although, of course, people tend to visit the parts near the two ends of that stretch, so if people just took the first stone they found, that would instead result in the main part of the bank becoming cut off from access on foot, as the sea broke through the depleted region at both ends and linked to the Fleet Lagoon, which would have the effect of preventing most other people from taking stones after perhaps only a few tens to hundreds of thousands of years. Either way, I don't recommend we do this. Of course, the other thing not everyone would do is to take just one stone. If removal of the stones were permitted, people wouldn't stop at one. They would cart away stones by the barrow load to decorate their gardens, or the truckload to pave their driveway, or multiple truckloads to do whatever they could think of doing with that amount, and that would make a difference. For example, as vast as Chesil Beach may be, and seemingly limitless, it is equivalent to just less than 5 times the volume of concrete used to make Hoover Dam. So it's conceivable that it could be impacted by human exploitation, and therefore I think the rule of zero exploitation is completely understandable. This is probably one of those exceptional circumstances where there is a genuine, non-fallacious, slippery slope to be averted by just saying no, not at all. I intend to respect and abide by these rules, and I encourage everyone else to do likewise. Anyway, in conclusion, you can indeed tell where you are on Chesil Beach and a lot of other things just by looking very intently at the rocks. And there are very good reasons why sailors in days before electronic navigation would want to know where they were. So I find it plausible that they might indeed have used the pebbles as a sort of GPS, that is, gravel positioning system. I hope our exploration of Chesil Beach has been interesting. Thanks for watching, and I hope to see you again soon.